Hello and welcome to the next installment of Engineering Fluid Mechanics, and this is a continuation of the open channel flow portion. Okay, so in the last video we concluded with the energy equation as applied in an open channel, and that was y1 plus v1 squared over 2g plus S naught delta x is equal to y2 plus v2 squared over 2g plus S sub f delta x, where that's the bottom slope and this is the energy slope. All right, well, so let's continue on with this and recall the definition of uniform flow. So uniform flow was defined earlier as the case where the depth doesn't vary with space, which would imply that y1 and y2 are the same in this equation, and the mean section velocity also doesn't vary with space, which would imply that the velocity head at 1 and the velocity head at 2 are the same. So in that instance, we have the property that S sub 0 equals the friction slope, and that is exactly the definition of uniform flow. But the friction slope from our prior diagram happens to equal the head loss per unit length. So let's look at the Darcy-Weisbach representation. Darcy-Weisbach model, as you recall, was for a pipe, head loss was some friction factor, length divided by diameter, velocity squared over 2g. Well, let's examine this. So if we had some analog to diameter, length is the delta x between two stations, and the v squared over 2g we already have an analog to, so we really would need an analog for diameter. Now remember, the Darcy-Weisbach equation was created for a circular pipe that's full, and the area of the full pipe is pi times that diameter squared divided by 4. The wetted perimeter of a full pipe, P sub W is equal to pi times the diameter. And one thing we've learned a few videos ago was the hydraulic radius was defined as area over wetted perimeter, which in case of a pipe is pi d squared over 4 divided by pi times the diameter. And so when you cancel out like things, we come up with the following property, that the diameter of a full pipe is 4 times the hydraulic radius. And this gives us an analog that we could use to apply Darcy-Weisbach to an open channel flow case. So the hydraulic radius, 4 times its value, plays the role that diameter did for a pipe. Now obviously they're not full, but we can substitute that and maybe we can find a correlation suitable for Darcy-Weisbach application. And in fact, that has been done by others, and it's reported in our textbook. So head loss per unit length equals the friction slope, which is equal to friction factor as yet undetermined, 1 over 4 times the hydraulic radius times v squared over 2g. So now we can use this idea in the Darcy-Weisbach formula and apply the Moody chart or even the Colbert-White or Swami-Jain equations. So the analogs are 4 times the hydraulic radius is used is analogous to diameter in Darcy-Weisbach. The roughness height over 4 times the hydraulic radius is analogous to the K sub S over D, which is usually set as epsilon term. And the Reynolds number is velocity times 4 times the hydraulic radius over nu, the viscosity. We combine all those and we can apply Moody chart, Colbert-White, Swami-Jain, in the same fashion that we did for pipe flow. There's an additional alternative mentioned in our textbook for rock channels. And in that instance, the friction factor can be represented as 1 divided by 1.2 plus 2.03 log base 10 of the hydraulic radius divided by the D84, so the 80th percentile diameter of the rocks in the rock bed, quantity squared. This one is a very specialized representation, so it would be applicable literally for rock channel use. Otherwise, if we're going to use a Darcy-Weisbach type, we would follow the process outlined here. Some alternative head loss models include Chesney-Manning, the Chesney-Manning model simply states that velocity is equal to some coefficient that's going to be dependent on channel properties and liquid properties times the hydraulic radius times the bottom slope. And this is for uniform flow. And there's a Manning, so this top one is just Chesney's. And there's Manning's formula, which has velocity is equal to 1 over n hydraulic radius cubed times the bottom slope. That's wrong. Velocity is 1 over n hydraulic radius to the 2/3 power square root of the bottom slope. 1 over n and c are not equal, but they're analogs. Square root of bottom slope, square root of bottom slope appears in both representations. And in this upper representation, this is radius to the 1/2 power, In this lower representation, this is hydraulic radius to the 2/3 power. Manning's equation is not a homologous equation, so it depends on units. So this is the SI representation. And the US customary representation is velocity equals 1.49 over n r to the 2/3 power s0 to the 1/2 power. Now let me rewrite both of these for clarity. By far the Manning's equation is the most used equation for open channel flow, at least for uniform flow. So in SI, velocity is equal to 1 over n, r to the 2/3 power, s0 to the 1/2 power. We look up n in a table. N is really described by channel properties, and we'll show you in a second. In US customary, velocity is 1.49 over n, r to the 2/3 power, s to the 1/2 power. If we multiply these by area, we get the classic slope area representation for discharge, which is Q is equal to area times velocity, which is equal to 1 over n area r to the 2/3 power s to the 1/2 power, SI units, or 1.49 over n a r to the 2/3 power s to the 1/2 power for US customary units. These are by far the most common representations in open channels. And as an aside, these slopes in Manning's equation are supposed to be the friction slope, but in uniform flow, friction slope equals bottom slope. So this is how they are commonly used. The coefficient n is called Manning's roughness coefficient, Manning's resistance coefficient, Manning's open channel flow coefficient. Goes by a lot of names. Key thing, the usual symbol is lowercase n, and the name Manning should be in the table. Is Manning's, I think it's also called Manning's flow resistance. These are looked up in tables. It's important that you be sure the table you're looking at is indeed Manning's equation, because both lowercase n's and uppercase n's are used for quite a few hydraulic models or fluid mechanics and hydrology things, and it's pretty easy to confuse them. So again, be sure that you're dealing with Manning's n. A good way to know that you probably have the right n is the order of magnitude of Manning's n. They come in numbers like 0.10, 0.05, are pretty typical. And that's for a lot of different channel types. Maybe as high as 0.6 in very specialized cases, but they're never they're never bigger than 1. So if you've looked up a Manning's n and the number is bigger than 1 or quite a bit smaller than 0.01, you're probably using the wrong table. That concludes this video. In the next video, we'll apply Manning's equation to a couple of example problems.